Good morning, everybody. I'm Philomin Juliana, doing my postdoc with Dr. Ravi at CIMMYT, and I'm currently working on genomic selection and implementing genomic selection, especially for grain yield and stem rust in CIMMYT's nurseries. So, how does this conference relate to genomic selection? So, delivering genetic gain in wheat, and how can we do that by genomic selection? First, I would like to just talk about what genomic selection is all about. So the concept of genomic selection is nothing but using genome-wide markers to predict the performance of lines without having to phenotype them, because now you'll be selecting based on their genomic estimated breeding values, and that could help us increase the rates of genetic gain and also advance generations rapidly. And to describe this process, so first, what we have here is lines which just have phenotypes and genotypes. And this we call as a training population. And then we use this data to train prediction models. And from that, you use the trained model to predict the values of lines for new germplasm, lines where you don't know the phenotype, and that will be our breeding population. And from that, we select lines that have high genomic estimated breeding values. We make crosses, and we advance generations. And this process can help us rapidly get varieties to farmers, and our ultimate aim is to deliver genetic gain quickly to farmers. And there's also another parallel path that you can do. You can evaluate the accuracies of the prediction models, as we see here, and I would call this as a pre-implementation phase, because before implementing any new technology, we would have to test it on our germplasm and evaluate how effective and useful that technology is going to be. So we are currently working on that pre-implementation phase before implementing genomic selection in CIMMYT's wheat breeding program. And what are the major steps if you want to implement genomic selection in any wheat breeding program? So the first step is to identify opportunities in the breeding program. Where does GS fit in the program? What are some of the traits that you can use GS for? And then is to evaluate the prediction models, genomic predictions for different traits, different populations, or different stages of the breeding program. And then evaluate the relative advantage of genomic selection over our current strategies or over phenotypic selection. And the next step is to implement GS for traits where you will see a very high relative gain compared to our current strategies. And this is the most exciting step to me. So there will be challenges in any research. And to me, that's the most exciting part. So I am here, and since there were a lot of challenges in our research, I'm here to say how exciting these opportunities can be, because when things don't work, to me, they are more exciting than when things really work well. So first, let us move on to identifying opportunities for implementing GS in CIMMYT's wheat breeding program. Just a brief outline of our breeding program and what are the potential stages which GS can help the breeding program. So GS is not a technique that can disrupt the breeding program, but it's something that can help increase the accuracy of selections in a breeding program. So the first stage, when we select parents, can we select parents based on their genomic estimated breeding values? How accurate we are in selecting parents for our crosses? Because many crosses, the breeder throws them away because they don't have just the right allelic combinations. So genomic selection can help you select parents well if you have the breeding values of the parents. And then, looking at CIMMYT's structure here, the early generations, and this is a little bit complex. Genomic selection is very beneficial if you do it for within family selections in early generations. But we do have a constraint here. If you look at the number of lines that we have in our early generations, they're going to be about 1 million to 1 billion plants. And these generations, we also have the lines segregating, and the high cost of genotyping here is currently a constraint for us to implement genomic selection in these generations. And also, the cost of line development to get to the F5, F6 stages is about $5. So how do you compare this against the genotyping cost of $20 currently? So we look forward to having cheaper genotyping technologies in the future that can help us overcome this challenge and implement genomic selection in these generations. And then, moving on to our head rows. So we have about 70,000 head rows, which are grown as small plots, and these are the pre-yield testing stages. And again, the high cost of genotyping here prevents us from using genomic selection. So what we do here is currently use pedigree and high throughput phenotyping data, which Sue will be talking about, and we use these two and we use a combination of both of these to predict lines at this stage. And then we move on to our yield trials, our first year yield trials, and we have about 9,000 lines in every nursery. And thanks to the USAID project and the DGGW project, as a result of which we were able to genotype all these 9,000 lines for the past 4 years. So now we have about 40,000 lines that have genotypes, and our objective here is to test genomic selection for grain yield and stem rust. And moving forward, the second year of our yield trials are known as the elite yield trials, and here we have lots of information, especially about agronomic traits, grain yield evaluated in 6 different environments, optimum, drought, and heat stress environments, and we have a lot of disease data and quality data in here. So how effectively do we use this data to test genomic prediction models? So that's one of our current objectives. So let's just move on to the results, what we have currently. So I've tested genomic selection in the elite yield trial stage, which has about 1,000 lines, and we've tested this for the past 4 years, so it's about 4,000 lines. And here you can see the accuracies both within and across nurseries. And on the x-axis, we have the 6 different environments that CIMMYT breeds for. So we have bed 5 irrigations, bed planting optimum irrigation, flat planting optimum irrigation, and we have reduced irrigations, early and late heat as well. So as you can see here clearly, the green bars show our prediction accuracies within nurseries. So these are nothing but cross-validation accuracies. You just use some lines from within the nursery to predict other lines within the nursery, and those accuracies were always close to 0.4. But the problem here is when we start predicting lines from other nurseries. For example, if you use data from a previous nursery to predict the next year how the lines are going to perform for grain yield in the next year, there comes a real challenge. So you can see those accuracies, those ones which are in red here, drop pretty drastically when you start doing this across years. And so we wanted to look at what is the effect of using different training populations. So as you can see from this graph here, I have shown the data for 2 different nurseries and bed and flat planting systems. And the green bars here shows the accuracies that you get when you use lines from the same nursery. The yellow bar shows the accuracies that you get when you use lines from a previous nursery. And the red bar shows the accuracies you get when you use about 3,000 lines from the past nurseries to predict this nursery. And as you can clearly see, you have a steep decrease in accuracies when you use other nurseries to predict this nursery. And that's a huge impact of G by E and environmental variations, which leads to a decrease in the accuracies when you start looking across different years. And we also looked into what results in these poor predictions across years. So as you can see in this graph here, these are the phenotypic correlations between the first year and the second year yield trials in 4 of our nurseries. And as Hans also mentioned very much about the yield stability, this is what you see. And as a breeder, we all know very well that some lines that perform well in the first year might not perform well in the second year. So when we train genomic prediction models using a variable data, using data that can change in the next year, that's a challenge that we currently have. And when you use it to predict, again, another set of lines, which are again variable, that's again a key challenge. So how do we improve this? How do we increase the reliability of our predictions or increase the reliability of our training populations? So this is what we do. To increase the reliability for a trait like grain yield that has low heritability and which is highly influenced by G by E, we need to have replicated data across environments in the training set. And I would also give a caution here. When we try to estimate single year performance and match that with the accuracy and correlate that with the true breeding value, that might not result in high accuracies just because the correlation can be just biased. We do not know how the same line is going to perform in the next year. But all we have is a phenotype as an estimate of the true breeding value. So that might be a challenge when you get estimates from genomic selection. And moving on, so we've also done genomic selection with stem rust in our EYTs, and here are the results here. And they look great and very promising to me. So what you have, the taller bars in every nursery here reflects cross-validations just within years. And the bars that are shorter are usually across nursery predictions. When you use some different nursery to predict this nursery, what kind of accuracies that you get. And stem rust being not so much influenced by G by E, you can see for this recent year that we have very promising accuracies. When you do cross-validation, you get about 0.7, and when you predict using a previous year, your accuracies are close to 0.6. And I would say that this is a real success of genomic selection for stem rust. And moving on, so genomic selection is not just about calculating prediction accuracies, it's about making real selections from the GEBVs that you have. So we looked at a selection intensity of 0.5, and here I've categorized the lines into 4 different classes. Lines that are not selected by genomic selection and phenotypic selection, and they are in red here, and lines that are selected by both these selection methods, which are in green, and lines that are selected just by phenotypic selection, and lines that are just selected by genomic selection. And as you can see here, about 68% of the lines will be selected between both these methods, and about 68% of the lines can also be discarded that are not selected by both these methods. And if you have a higher accuracy, then your chances of having more lines that are selected and discarded that are in common between these methods are also high. And the reason we wanted to do this is for a trait like grain yield, where your variability can be narrow, let's say between 5 to 8 tons. You can't always expect the predictions to be very close to your true breeding values. For example, let's say your true breeding value is 5.4. How often do you get the same 5.4 when you have to make so much spatial adjustments and other adjustments to the data, especially if you're running yield trials? And that's the reason we wanted to go beyond looking at prediction accuracies and look at how effectively we can use the prediction accuracies. And there's another interesting thing that we observe in our nurseries, as Hans also mentioned, CIMMYT pedigrees are really excellent in predicting lines performance. So we wanted to look at what happens if you have different family structures in populations. So the figure on the left, it shows you lines which have no full SIBs in the population, but just has one individual per cross in the population. And I've compared the accuracies using genomic prediction, which are the ones in red, and pedigree-based predictions. And you can see clearly that genomic predictions give slightly higher accuracies than pedigree-based predictions, especially when you're dealing with lines that might not be highly related to each other. But what was really interesting to us is a figure on the right, where you can see lines which just have at least one full SIB in the training population. So you have one sister line in the training population, and you are using the information from that sister to predict other sisters in your validation population. And as you can see here, from our expectations, the pedigree should not perform as well as the genomic relationships, because all we get with the genomic relationship matrix is the identity by state relationships or the realized relationship between the lines, and that should be much better than just using the pedigree, which might just tell you 2 full SIBs are related by 0.5. But what we observe in contrast is that the pedigree does as good as the markers if you have just one SIB in the training, full SIB in the training population. So we wanted to go ahead and look at what is the family structure in our nurseries. And what we found out was that half of our lines, about 50% of the lines in each nursery, were just single lines that had only one individual per cross. And the remaining lines that had at least one full SIB in the nursery had minimum variance for grain yield, just because they were selected lines. They were selected for superior grain yield. So these lines, rarely, there's no chance that there might be a high Mendelian sampling among these full SIBs. So that's what we found out. And this is something that is really important, that we test family structures in our populations and don't use GS on selected populations, because then it's not going to have any scope of outperforming pedigree-based selections. And that's a paradox here. So some of our well-replicated stages for training GS models had little advantage over the pedigree just because of the family structures and selection in these populations. So we also looked at the marker density. So all we use here are GBS markers, about 2,000 GBS markers. And so we categorize the markers by removing markers that are highly correlated. And as you can see in the graph here, about 250 markers are enough to give you the same accuracy as using 2,000 markers. So the implications of this is we might need better marker platforms or higher density marker platforms because that can have a serious impact on your prediction accuracies. And we also looked at the relationship of grain yield and other agronomic traits. So grain yield is not a trait that is by itself, and phenology, lodging, and other traits can affect grain yield. So this is our correlation between these different traits and grain yield across different nurseries. And as you can see, some of these correlations, the trends and the correlations can be quite variable across the years. And it's very important that we include these traits in modeling. And so we are now looking at multivariate models that slightly give higher accuracies over just using univariate models for grain yields. And that's the last thing that we've done. We've also combined pedigree and genomic relationship-based predictions with high throughput phenotyping data. And we've done this, and I'm just showing you two different environments here, the drought-stressed environment and the heat-stressed environment. And we've identified a combination of using the pedigree relationships, which is the last one, the green bars are the last ones, and G and DVI, just use HTP and pedigree, and that's going to give us quite similar accuracies to using genomic and HTP data as well. And we also have done genomic predictions for quality, and here we see a very good advantage of markers compared to using pedigree. And quality is a trait that is still not, some of the traits mentioned here, like the alveograph, flour protein, flour yield, loaf volume, and mixing time. And all these traits, some of them are complex, for example, flour protein or flour yield or loaf volume, but you still get very good prediction accuracies across nurseries for quality. So that's very interesting and very promising, and a PhD student at KSU, Emily, is working on quality predictions. And so what do we do with all this data? So now we have finished our GS 1.0, we've finished testing our different models, and what's the way forward? Our next step is to go forward to GS 2.0. So what do you do with all the resources that are generated as part of the projects? So you can make a lot of informed crosses, know the GBVs of the parents, and then make crosses based on the known information. And then we have a lot of information on the markers, and we have to validate the lines and validate those markers in the lines, and we can use them. And there are also big data that we have for the hedgerows, and our objective here is to use some of a very good recommender system, the item-based collaborating filtering approach that Amazon and Netflix uses to predict grain yield using some of the HCP data that we have on about 50,000 to 70,000 lines. And we're also looking forward to scale up selections and yield trials. And as I had mentioned, that quality is very well predicted using genomic predictions. And our quality specialist says that he's spending about $61 for 1 unit of evaluation for quality. And that's going to be a huge savings if we can scale up selections to a previous generation. And just the last slide here, envisioning genomic selection for the future. One thing that we have to note here is that breeding is not just about single traits. We have different traits here, all evaluated in our EYTs. And as you can see, some of the correlations can be negative, positive, and you have all sorts of things. So I would like to stress that we need a broader perspective, an application perspective for GS, and understand its fit in the breeding program. And we have to just face challenges undauntedly, because challenges are always fascinating to the mind researcher. And with that, I would like to acknowledge the BGRI, the DGGW project, the Bill and Melinda Gates Foundation, the USAID project, and all our collaborators from CIMMYT, Jesse from Kansas, and the Cornell DGGW team. And I would also like to specially mention Dr. Vijay and his contribution from Cornell Sadhguru Foundation. These were key contributors for my career as a plant breeder, the Monsanto's Beachland Borlaug Fellowship, and the WIT Award, and also a special mention to Kathy Gan for the great support she has been providing to young scientists and the opportunity to be a WIT scientist today. Thank you very much.